Good morning, 3U chemists. So today we're looking at, again, gas laws, surprising. And as a quick review, we have seen that these three gas laws right here, Boyle's, Charles, and Gay-Lussac's, all go together to make something called the combined gas law. Okay. And then it's been introduced that there is another law called Avogadro's law that we can put in there too. So we're going to get an extra big law with 4 laws altogether. And it's going to be called the ideal gas law. So this will be 4 gas laws. And as you can see, the extra gas law is right here. Avogadro's law basically says that if you increase the number of moles of a gas, the volume is going to get bigger. It's very much like blowing up a balloon. The more gas you put in the balloon, the bigger your balloon is going to be. So it looks like this by itself, but we rarely use it all by itself. It's usually just incorporated inside the combined gas law to now give us the ideal gas law. So as before, an initial set of conditions is equal to a final set of conditions because it is a constant. Now, when we're talking about the ideal gas law, we've kind of replaced this constant with the letter R. So constant is now going to be called R. Not really sure why. Now, you might be wondering why we're talking about ideal gases, because later in your science studies, you might hear about something called a real gas. Ideal gases are just saying they obey all these laws perfectly. And the big thing is with an ideal gas is that it is always a gas, no matter what you do to it. Well, we know that isn't true. A real gas, if you put enough pressure on it and cool it enough, you can get the gas molecules to go together tightly enough that they're actually attracted and you can liquefy it. So picture your propane gas tank for your barbecue. If you pick it up, it sloshes around because there has been so much pressure put on when the gas was put in there that it has actually liquefied. Same with a butane lighter. You can see the liquid. So those are real gases. And obviously, if they can be liquefied, how on earth are they going to obey these laws that we've come up with? So when we talk about ideal gases, we're sort of pretending that the gas could never be turned into a liquid. In other words, the particles can never be attracted enough together to be liquefied. Okay, so what you will often see, and I know you watched a video earlier, that this ideal gas law is usually written like this. So I've taken this PV over NT equals K, I've put R in for K, and this is how you usually get this equation. Okay, so let's just review. P is for pressure, and you have 3+ choices of pressures, like kilopascals, atmospheres, millimeters of mercury, torrs, PSI, that's 5 already. Okay, volume always needs to be in liters, no exceptions. N is going to be your number of moles, not mass, moles. The constant is going to have 3 choices because depending which unit you use for the pressure in a question, you're going to select a different R value. And then T for temperature absolutely has to be in Kelvin. Okay, so you do not need to know this in any way, but I'm just going to show you how we've come up with the different values of R that you might select. So standard temperature and pressure is something that happens when we are basically at sea level pressure, which again with the 3 different units could be 101.3 kilopascals, could be 1 atmosphere, could be 760 millimeters of mercury. And we have to be at 0 degrees. Celsius, which of course is going to be 273 Kelvin when we add it. So at those conditions, we have already worked out, like chemists have worked out, that if you have 1 mole of any gas, as long as it's ideal, it's going to take up 22.4 liters of space. Doesn't matter if it's carbon dioxide, oxygen, whatever. So using that and then solving for a value for a constant, we've done it 3 different times. So this is if it was atmospheres, 1 atmosphere. This is in millimeters of mercury, so 760. And this one here is for kilopascals. And then here is your magic constant. And you can see that the units are quite ugly. It's, kilopascal liters per mole Kelvin, or millimeters mercury liters per mole Kelvin, etc. Often when you use this in a problem, you're not even going to write that big ugly unit, but you will have to select the right constant to use. And again, you do not need to memorize those. Those would always be provided for you in any course. Okay, so a quick example of a problem. So essentially, now what we're saying is if we know 4 of the quantities for any gas, you can solve the 5th. And it doesn't matter. It can be any combination of temperatures, pressures, volumes, moles. And the one new thing you will always be able to know or look up is R. So here we have 0.39 moles of water vapor. It's 22 degrees, 125 kilopascals of pressure on it. How much space is this gas taking up? Okay, so the question is volume, moles, 0.39 moles. As I said before, it's a good idea to write things out and then you'll hopefully recognize what formula you're using. Temperature, 22 degrees Celsius. We need to add the 273, which is going to be 295 Kelvin. Pressure is 125 kilopascals. So then right away we want to figure out, well, what gas constant should we use? And we're in kilopascals. So if you go up here, we're going to use 8.31 kilopascal liters per mole Kelvin. I'm just going to show you, what it looks like when we put that in, but often you would not write that unit. Okay, so if our standard formula is usually, provided like this, PV equals nRT, if we want volume by itself, we're going to have to divide pressure out of the left side and the right side of the equation. So it will be nRT divided by pressure. And then plugging in 0.39 moles times 8.31 kilopascal liters mole Kelvin. I'm trying to squeeze this all on here. And then we have temperature, which I need 295 Kelvin. Oops. Always turn your ringer off. Okay, and pressure, 125 kilopascals. Okay, so on your calculator, you're going to want to put 0.39, multiply by 8.31, multiply by 295, press equals, then divide by the 125. And let's just take a look. Moles is going to cancel with that mole on the bottom. Kelvin is going to cancel with that Kelvin on the bottom. That kilopascal on the top is going to cancel with that kilopascal on the bottom. We're left with liters, which totally makes sense, being as we're solving for a volume. So 7.64 liters is what you should get. We're only allowed 2 sig digs tops, so 7.6 liters. So that is how much space water vapor would take up under those conditions. And again, it wouldn't matter what kind of gas we were actually talking about. That is the volume it would take up. Okay, so you'll get a couple practice problems, and that is it for today.